Hey, g'day, it's Prezzo here, and I'm starting a new project today. But before I do that, I thought I'd address a few comments that came out of the last series of videos that I did on building these replica Art Deco digital clocks. And one person commented that they'd like to see both the clocks together. And I did make two of these clocks, and one of these is for a gift. And well, here they are. They're both running. Interestingly, if you check the seconds on both clocks, you see that they're not synchronized, which I found rather fascinating because they are connected to the Wi-Fi and they get their time from an NTP server. And I cannot account for why they're not running exactly synchronized. However, the location where I have these at the moment is a long way from my Wi-Fi extender, and the signal here is a bit spotty, so I'm guessing that they refresh every now and then and correct their time base. And I have noticed that occasionally they run in sync, and then you'll find this one is fast, that one's slow, and then vice versa. So other than that, I have no answers. And another question that came up was why was it necessary to put 10 of these edge-lit panels in every single place in the clock? And if you think about it for a while, this placeholder here never gets past 5, nor does this one, and in the hours it never gets past 1. So my answer is that these Lixie display units were designed by somebody else, a gentleman named Connor Nishijima, and when he designed these were intended to be used as just digital displays, not necessarily as a clock. So each individual unit, and he did sell them as single units, could be used as a temperature display or an RPM counter or something like that. So you'd assume that in that role you need to have every single display capable of showing all 10 digits. In a clock, of course, you don't get that. So that's my answer there. And I want to move on now to a new project, and it's a Victorian style engineered steel bridge. Logical progression, isn't it? Yep, and admit it, you were thinking the same thing, weren't you? But that's where we're going with the next project. Now I said bridge, it's really a footbridge, and it's intended just for crossing a narrow creek. But that's where we're going. So let's go and check out the site, and then we're going to have a look at some materials. So let's go for a bit of a walk down here to where this wonderful civil engineering project is going to take place. Now, as you can see here, it's extremely dry at the moment. In Queensland, we've had record temperatures for over a month now, and almost no rain where we're living at present. And this creek is a seasonal creek. It runs into a man-made dam. And about 25 years ago, I cut down a tree, split it in half with a chainsaw, and just put the two halves across the creek here. And well, that just served as a crossing point. And as you can see, it sort of failed catastrophically while I was walking across it at one point. And the other half, I'm not willing to put any weight on that at all at the moment. So we're going to have a beautiful new steel structure to replace this. It's going to be anchored on both sides using concrete footings, and I think it's going to look great. Anyway, let's head back up the shop and have a look at the raw materials. Okay, this is where this whole project got started. A friend of mine made a bridge for a client, which he called a Monet bridge or an arch bridge. It was much wider and a longer span than what I'm doing, but at the end of the job he had 4 pieces of stock left over, and he had the original stock rolled to his specifications, and it came out with the radius that you see there. The 4 pieces have been welded into 2 pair. So, is that right? No, it's been welded into a pair of spans. So there's a weld right at the center there, and although in terms of engineering that's a bad thing, this is a footbridge. It's going to hold 2 people maximum, so I don't think that that's going to be a problem, provided my welds are good enough, and let's see about that. However, this is what forms the main span across the creek, And the other material I'm about to show you is going to form the good looking bits, the nice stuff that makes it look like an engineered bridge. So let's have a look. Alrighty, well here's the drawing. Now I did this in SketchUp just simply because it was easy. I started off with Autodesk Inventor and I found it was just way too difficult to get the constraints that I needed. So SketchUp is easy, but the downside is that it's much more difficult to extract good 2D engineering drawings from SketchUp. But I got enough to be able to do this. Now my inspiration for this design was those beautiful Victorian steel and iron bridges which were a product of the Industrial Revolution. And there are plenty of examples of these all over the world, both as footbridges and traffic bridges. Here's one on the Yarra River in Melbourne, and here's another one from Cataract Gorge in Tasmania. And I love the look of the Victorian style engineering used in those. So these diagonal braces and the webs in the centre, that's the sort of look that I was after. And I really wanted to get this round head, hot riveted looking construction for the bracing, and for various reasons that didn't work out, and I'll show you my various failures in trying to make these rivets in a minute. But there it is. It's basically a lot of welding and a lot of sort of plasma cutting and fabrication. So yeah, it's going to be fun. Now, don't laugh, but here are my attempts to make forged round head rivets. Every one of them was a failure, and I'll show you the tools that I made and then we'll discuss how we're going to get around this problem. Now my research led me to believe that all you needed to make forged rivets was a dolly, or I think that's called a monkey tool, and a rivet set. And I made both of these out of some heavy steel sections that I had. Monkey tool here started off being drilled out at 8mm for 8mm hot rolled steel, and I got these bright red with an oxyacetylene torch and then just sat it in there and tried to form the head with this rivet set. So this is made of 4140 steel. It was drilled and domed out using a round end mill, and I didn't harden it, I just left it as it was. And well, it's a complete failure. The problem is that you get this stuff red hot. By the time you get it in the tool, which is cold, it takes all the heat out of it. This also removes a lot of heat from the steel, so by the time you get around to bashing it with a hammer, it's already partly cooled off. So I changed to 10mm diameter steel, thinking that this would hold a little bit more heat, has more mass, but it's the same problem. You get it red hot, by the time you fiddle it into the tool here, it's already starting to cool off. I used the biggest hammer that I could get, and I tried to get it done as quickly as I could, and most often what happened was it just simply pulled the steel off center, and although you got something that looked like the right shaped head, it wasn't concentric with the stem of the rivet. Now I did think about making just like I think they call these blacksmith's rivets, just with a flat head, but it wasn't the look that I was after, and I still had this problem where they were not concentric. So that was a complete failure. So what I've decided to do instead is to use these galvanized cup head bolts. Now, you know, from a distance, if you squint your eyes, they're going to look a bit like rivets. They're going to be nutted up on the inside of the handrails where you're not going to see it as much. And the square head, if you measure across the diagonal, is about 11mm, it's just over 11. So if I drill an 11mm hole in one of the parts, it'll pull down into that and stop it from rotating as I do up the nut, I hope. So that's the plan, and these being hot galvanized, they should stand up to the weathering process. So I've got that sorted. Now let's have a look at the materials that we're going to use for the bridge. For the handrail supports, or I think they're called stanchions, we're going to be using this stuff. This is Duragal. It's a commercial product, comes already galvanized, got a beautiful coating on it, and it's 50 by 50 by 2mm square hollow section. And I chose this because, well, it's got a nice finish, but also because of its corrosion resistance. Now, for the same reason, for the diagonal bracing, I've got this is 25 by 5, and this is hot dip galvanized. And although the finish isn't as brilliant, it's probably going to be a lot more durable. So I've got enough of that to do all my diagonal bracing. Now, there are some lugs that need to be welded to the stanchions for the diagonal bracing. And for that, we've got, this is 50 by 5mm hot rolled steel. Unfortunately, I had some of this on hand and it's not galvanized, so that could be an issue. And it's also going to be used for the handrail mounting points at the top of the stanchions. That's it. So these are relatively small parts in the structure, but just the same, I'm going to be really careful about using a good corrosion resistant primer for all of these parts. Same goes for the gussets. So where these diagonal braces cross over in the center, we're using 6mm hot roll steel plate, and this will need to be cut with the plasma cutter to a template. And as it turns out, these two outer ones are quite different to the middle one, but I've got full-size drawings of that, so I can use the patterns. I'll just make them out of plywood. So that's it, that's all our materials apart from our arched sections, and well, let's get started. It's a civil engineering project. What more could you want? Okay, stop laughing, but this is my setup for doing the fabrication of the bridge span. Now, I don't have a nice big dead flat fabrication bench, and the floor of my garage is not even close to being level. However, I have set up one of the arch spans on the sawhorses here. I checked to make sure that it is level, and I had a piece of this material left over, the square stock for the stanchions. So this is my datum. I can set out my stanchion positions. I hope I'm saying that right, stanchion. I'll have to look that up. We'll set out the post positions, and I can do all my measurement off this piece here. So I've got everything clamped in place. The posts are level, they're parallel to each other, and they've got temporary supports at the ends, just so I can get the tacking and the welding done as I go. Now, a caveat before we go any further. I am not a welder, not even close to being professional. So if you see me welding and you're thinking that I'm using incorrect technique or incorrect speeds, yeah, probably am. I can do functional welds. They're not pretty, but they'll do the job. Okay, once I've got these square to my datum, I've just got them clamped off, and then I've got to get them level, and then they can be tacked. These are the two outer ones, and then I'll go along and double check to make sure I've got the correct spacing all the way along. I think it's 1 meter spacing between the vertical uprights. You should be able to see I've got all my vertical posts clamped and level and parallel. So I'll finish tacking all of these off at the base, and then we can do our diagonal bracing. One of the jobs I need to do before I disassemble all this is to mark out the length of each one of these stanchions. Now, I checked the pronunciation. It's called stanchion or stanchion if you're posh. But what I need to do is to mark out a curve at the top which is concentric with the curve of this bottom span. So that will mean that I need to be able to work off this bottom curve here. So what I've made is a trammel And the Trammel has a fence at the bottom here which has 2 points of contact. So as long as these 2 points are kept in contact with that inside of the curve, then the straight edge is always going to point to the common center to keep those 2 curves concentric. So all I need to do is to run this along and then mark out at the top of the fence there, or the top of the straight edge, and with a Sharpie just mark off that curve. So if I get all of that done, I can then also mark out where the lugs go for the cross bracing. So that's why I've got to get this done now. So that's my curvature there, and I'm going to have to cut that off later on with an angle grinder and do the same for all 4 posts or stanchions, and then we're ready to go ahead and mark out the position of all the lugs. Now these little gadgets here, I call these the ears. I'm not sure if that's the correct technical term, but hey, it's my bridge, I can call them whatever I want. And these are used to weld to the vertical uprights, or the handrail stanchions if you like, and the diagonal stays will be bolted to these. Now I'm cutting them from this stock, which is 50 by 5mm hot rolled steel, and I've got a few offcuts of this so I can cut one at either end and then cut the angle to suit. Now, to cut that radius there, you could use an angle grinder and you could sort of grind it around, get it approximate, and it would look fine. But it's a bit tedious to do it that way. Now, I'm lucky enough to own a small plasma cutter. I think I paid about $1,100 for it, and I bought it specifically for a job I was doing for a client. But in the home shop, they're a really handy little gadget. It gives you the capability to be able to cut steel up to around about 12 or maybe 16mm at a pinch, but you can also cut aluminium, copper, stainless steel, and you can cut very thin sheet without the risk of too much distortion. So for a home enthusiast, I think they're a very, very worthwhile addition. And I made a simple jig which bolts through that 8mm hole there, and this forms a guide for the tip of the plasma torch. And I've machined this so that it gives me the correct offset to cut that radius. So it's quick, it's simple, and gives you a fairly clean result. Just needs a bit of a grind on the linisher to finish it off, and I also cut the angle on the end here with plasma. So I'm going to drill an 8mm hole at both ends of this stock, and I can cut 2 ears out of each piece, and I just gradually make them shorter as I go. So let's go ahead and get these holes drilled and do some plasma cutting. Happy days! Just using my Jenny caliper here to find the centre. When I punch these, I'm punching a little bit back from the end of the stock, so that I've got a little bit of waste left on the end of the stock when I cut the radius, just to make sure I do get a clean cut. Of course, it's really important that you get your centre punch marks accurate. when you're cutting a radius on stock that's already to size, if you get it wrong, it's going to look a bit dodgy on one side. Right, so there's my guide, the plasma torch, just run around that end there. This is the plasma that I'm using. It's a Univig Razor 45. Really simple to operate. You just got a current control on the front here. All you need is compressed air. That's it, and you're ready to cut steel. Most of these plasma torches will come with some sort of a guide on the end here for running against a straight edge. It's just a friction fit. This application, I take it off, I just run the end of that nozzle against the guide to go around the radius. And the thickness of that guide there keeps the tip of the torch the correct height above the stock. Pretty easy to dress that slag off, and I'll give that a grind and a linisher to finish it up. But certainly way quicker than any other way I could think of. Eagle-eyed amongst you will notice that my fixture has changed. I made this centre stud out of aluminium, and I was undoing the nut on the other side and snapped it off. So made a new one out of steel like I should have done the first time, and to add insult to injury, I was trying out a new pair of goggles and I put the tip of the torch on the edge of that fixture there and blew that out. So yeah, having a good day. So you can just check these with that little timber template just to check the radius. And that's the one that I miscut with the plasma torch on the template. I'll just weld it up. To cut these angles, I put the tip guide back on here and I just clamped a straight edge parallel to that stripe line. The offset is 12 millimeters, so I just got a piece of wood here, the correct width. Give me the offset line, and piece of cake, just cut through it. And you do get a really clean cut that slag that's sticking to the back, you just hammer that and it comes off, and just give it a light grind and it's done. So with that slag, you just give that a bit of a hammer on that edge, and it just breaks off like that. And there's almost no other preparation you need to do for that before you weld. And good thing too is that these things aren't particularly hot after you've done that process. It's not like oxyacetylene where you've got to preheat the edge and then cut it. The process is so quick that there's almost no transmission of heat into the part. Anyway, I've got stacks of these to do, but you've seen how that works, so we'll catch up when I've got all these done. I want to drill and radius one end of each one of these diagonal braces so that I can actually get the other position, the other end, from the job. So I'm just going to glue this up, and we'll drill an 8mm hole at the center, and then I've got a little gauge here, or a template that I can use to get the radius. This will drop through the 8mm hole, and I'll scribe that, grind it. And later on, one of these holes is going to have to be opened up to 11mm to allow that cup head bolt, or the square on the cup head bolt, to go right through. So I'll just let that dry. Okay, I'm just going to use the finely ground and machined point on the end of my digital caliper to scribe that line there. No, I'm not, just kidding. I hate seeing that. Look, buy yourself a pair of these are called odd leg or Jenny calipers, and the hooked point rubs against the edge of your stock. Scriber point marks the line, and you just simply mark it from one edge, flip it over, do the same from the other side. If the scribe marks coincide, you've got a dead center, and then you can just carefully scribe your mark from both the edge, the long edge, and the short end. There's your center point. So remember, these things, these are for measuring, not marking out. Okay, drill that 8mm. So this template here is an 8mm spigot to fit through the drilled hole, and this outer diameter here is 25, which is the same as the width of the stock. So just scribe that around there. Okay, grind that to shape, and we'll do that on one end of each of the straps. So the next process is to get all of these little lugs or these ears attached to the stanchions, and I need to be able to get an offset from the bottom of the stanchion to the corner of that lug, and then hold that right in the centre of this 50mm square post. So I've marked out my offset for the face of that bracket, and I've clamped that to a piece of angle. The angle's clamped to the face of the stanchion, and I've put the lug in there, and I've already pre-drilled this length of material for the diagonal brace, and that just allows me to check to make sure I've got the correct one of these in the correct place, because there are 3 different types that need to go on. So I'll go ahead now and tack all of these little brackets on, and then I can set out the length of my diagonal bracing. Alrighty, well that takes care of the first pair. So I go ahead now and get all the rest of these on, and then we can start setting out our bracing. Well, as you can see, I've got all my diagonal braces now cut to length, and they're just sitting there at this stage. And the next thing I need to do is to get a transfer punch and punch through the position on the back of that bracket to the underside of that diagonal brace, and then I've got to drill these. But I'm thinking that before I do that, I really need to bite the bullet and just do all of these welds, get this fully welded up. Now ordinarily I wouldn't do that. I did say I was going to dismantle these stanchions and weld in the brackets and then put it all back together again. And that was just me, you know, second guessing myself and figuring that I'd probably get it wrong if I try and weld it all up at this stage. But you know what? I've decided to bite the bullet and go ahead and get this welded. I think before I do that though, I'm going to put a brace along the stanchion. So I'll clamp that long piece of tube to the stanchions, double check it all before I do any more welding. So that's the plan. So I've just gone through and checked all of that. Everything seems to be parallel and flat. So no more faffing about, I've got to do these welds. Rubbish. That's shit too. That's acceptable. Just. Second rate. Marginally better. Look at that. Better clean that. Well, just about every one of those is terrible. I mean, they're going to hold, that's not a problem, it's just that they look bad. Oh well, lots of grinding. So I'm just bolting one end of each diagonal brace just lightly to keep that one centered in position, and then we'll look at the other end. So at this end, what I need to do is to mark off the position of the radius. So with my template that I made up for putting the radius on this end here, I just put that through the 8mm hole and just scribe that off. Okay, that gives me a mark on both sides, so it's sort of symmetrical around that hole there. And then I've made a tool which looks like that. So it's got a conical point. This end is 8mm diameter, so that'll fit through the existing hole in either the lug or the strap. And I've made that out of silver steel, and I've hardened and tempered that. So that just goes through that 8mm hole, fits flush with the surface of the plate. Put that over the top, and then looking down from where I am, I can center that strap on the pair of marks that I've already put on the bracket. And we do then is just belt that with a hammer. Okay, there's my center punch mark there, and I can drill that now 8mm diameter and mark out the radius on the end of that strap and get that ground to the correct shape. This is one of the sections on the end of the bridge with all the diagonal bracing now bolted in place. And the way this works is that one of these diagonal braces fits on top, the other one fits underneath, and there's a space in the center here for a piece of 6mm steel plate, and that will be cut and profiled to simulate a sort of a, what would you call it, like a web bracket, and it will have two cup head bolts fitted in each one of these diagonal corners here. And you can see here I've got, in this case, the cup head bolt on the top passing through the ear, the straps on the back, and there's a nut underneath there to hold it all in place. And on the opposite one, it's the other way around. So now the diagonal brace is on the top, and the cup head bolt fits down tight against that. So these holes have been drilled out to 11mm, and that clears the square on the end of the cup head bolt. Nut goes on the other side, of course. And if I get all of these sections done, that will at least hold everything more or less in place, and I can go ahead and turn this over and weld the other side. So at the moment I've got a piece of angle here clamped down just to provide some spacing support, so I can go ahead and get these straps drilled. Sadly I'm going to have to finish this up here. I thought I was going to cover a lot more in this video. Unfortunately my computer had to go away for servicing, and I was continuing to shoot as I built the bridge, and I assumed I was going to fit a lot more into this first episode, but that's not going to happen. But join me on the next one, because we're going to look at making these little decorative webs that go in the center of the diagonal bracing, and that was an interesting job in itself. And it was more about making sure that what was rather an odd shape was going to fit perfectly into all of these drilled holes. We're also going to turn this now two-dimensional structure into a three-dimensional framed bridge. So join me on the next episode when we continue with this civil engineering saga. So for now, thanks for watching.